Alright, good afternoon. I'm going to make a series of videos about complex circuits. So this first video will talk more about just analyzing a straight parallel circuit. So we started doing this in class today, so I'm just going to finish up on some of the things I wanted to point out. So, here we go. There we go. So, as you can see, as I talked about, a series circuit has one loop, one current, different voltages. Parallel doesn't have one loop. You have a choice for the electrons to go through. So we actually have different currents. But if you notice, every part of these resistors here are connected to the same part of the battery. Or in other words, if you look at this resistor right here, it's connected to the negative end, and so is this one, and so is this one on one side. And their opposite side is connected to the positive end. So what that means is they all see the same voltage. Sorry. In that case, let's just go back to this, like that. So, as stated in class, we're standing in line, we're all holding hands at the same point right there. So we need to find the current. So what we derived in class is that we can actually combine these as a resistance equivalence of all three of these parallel resistors into one that represents the three of them. And when we did, what we found was that the resistance equivalent of a parallel circuit is the inverse of the sum of each resistor. Now notice that this is also an inverse, so you have to be careful. Let me just demonstrate really quickly what this means. So if we looked at this, I wanted the resistance equivalent, it is set up like this. Req is the following: 1 over 6 ohms plus 1 over 6 ohms plus 1 over 6 ohms. Okay? So if I do that, I still have this as an inverse. And I'm going to do that right now on my calculator to get an answer. Okay. I get a decimal of 0.5. But notice this is not the resistance equivalent. This is actually the inverse. To solve this, I actually have to take the inverse of the inverse. Or in other words, I literally have to solve it like this. And when I do that, I finally get the answer that we want, which is the 2 right here. So 3 resistors in parallel represent one smaller resistance. So anytime you go from, a resistance, or anytime you have a circuit with parallel resistors, you're always going to get smaller. So parallel, your R's are small. And as a comparison, remember our series, they actually got to a larger value than what you started. So if you start with 6, you're going to get something lower than 6 in the parallel. With the series, if you start with 6, you're going to get higher than something. So this is higher than the original resistance. A quick trick with this, this is perfectly fine. The way I do it step by step in my calculator, by the way, let me just get a clean screen for this. So I'm just going to do that and just get a clean screen. By the way, you can also do this on your notes. I should have said to take out your notes and you can follow along. Is instead of writing it like this in my calculator, the way I do it like this. Now you have a symbol on your calculator. So on your calculator, your graphing calculator, you have a symbol that looks like that. So what I do is I press 6 and then that symbol, just like that. So I don't have to worry about typing in parenthesis 1 over this, parenthesis plus. This is just a fast way. And then what I do is once I get that answer, I do it again. It just makes it a lot quicker. So that's a technique you can use to help, expedite these processes. Just checking Right. So, we're going to use the property of resistance in parallel to solve this. So why don't you pause the video and see if you can solve this on your own. Okay, so I assume you tried it, and when you did, you should get 4.29. Where you get that from is like this. You're going to do 1 over REQ is equal to 1 over 17. I'm going to ignore the units, so these should all be in ohms, but I'm trying to expedite this. So I'm going to do that trick, 17 inverse plus 12 inverse plus, we got 11 inverse, 4.29. Well, this gives me 0.233. Now remember, this is not the answer. We need to solve for this. And then when I do, you get 4.29 ohms, just like that. So technically this is inverse ohms, and we want it in ohms, like that. Moving on. So now that we have the REQ, or our R, and we know that the voltages are the same, we can actually find the current in our system. Well, I guess we'll start from the REQ. So from right here, we can actually find the maximum current in our battery just by using the REQ. So let me take a step back. I just wanted to see where my slides were going. It's too far back. Previous. I'm sorry. Oh, previous. There we go. So when we do this, so now that we have our resistance equivalent, which we found was 4.29 ohms. I, and this is for our simple circuit, which means this is the I that the battery sees, more or less. It's going to be V, which is 60 volts, over R. So 60 divided by 4.29, you get I is equal to 13.986 amps. I'm just going to go for rounding it to 14 amps, straight up. So this is the current basically the battery sees, because it's the single current that's going around. And remember, the battery doesn't know that there's 3 resistors here. It kind of sees this case right here. Remember that number, because now we're going to solve for the currents in each of the branches. And that's our next step, which is here. So like I said before, we know that voltage for each of these are the same. What I mean is, the resistance 1 will see a voltage of 60 volts of the voltage that they're all connected to. In this case, it happens to be the battery, but that's not necessarily always true. But for now, this will suffice. So this is 60 volts. This is 60 volts. This is 60 volts. Which means I can find, I'll call this I1. I'll call this I2. I'll call this I3. So I1 is V1 over R1. I1 is 60 volts divided by 17 ohms. 3.53 amps, just like that. And in the same fashion, I'm going to do the 3 of them. So this will be set up as 60 divided by 12. This will be 60 divided by 11. This should be volts, sorry. Just gonna write over. Should be volts, that's fine. So 60 divided by 12 gives us 5 amps. 60 divided by 11, 5.45 amps. Like that. And we should find that due to conservation of charge, now I say conservation of charge because remember, current is our charge in our system, right? Charge per time. Charge must be conserved. Sorry. Conserved, there we go. Which means that if I have 10 charges, they'll break up into different parts. Maybe 5 go here, 2, and then 3, but the total that goes through has to be the same as what it started. So we should verify that. In other words, that the total charge starting from the battery should equal the sum of these. Let's do that. Now remember, we got this value as 14 from the previous slide. So 3.53, this is just a way you can check your work. You don't necessarily have to really check it. It's a good way to see if you're right, but also it's a good way to find a missing current if you are missing a current, like an AP open-ended problem or a AP like multiple choice. So I enter this into my calculator, sorry there, and I get 13.98. And as you can see, this is pretty close to our, 14 right there, just like that. So hey, it works. Or in other words, what we could say in a more physicsy sense is charge is conserved. That the 14 amps breaks up into different branches from here to here. And right, we have the same voltage. And that's what we did. And that's exactly what we just verified, is that the I total, the I through the battery, should equal the 3 right there. And that is it for the just doing a straight series, straight parallel circuit. So in summary, current is the same with series. You can calculate the voltage drops between each resistor with I and R, and the total voltage is the sum of the resistor voltages. And the opposite's true. The voltages are same through all the resistors in a parallel circuit. You calculate current, V equals R, V divided by R, and the I total is the I of the resistors. And generally, with a series circuit, you're adding, or how should I say, not adding, but your R equivalent is always bigger. Oops. Let's go to this. I'm almost done, I promise. Previous, there we go. Back to here. So this, the resistance equivalence for a series is always greater than the original resistors in your circuit, always. And for here, the REQ for parallel is always smaller than the original resistors in the circuit. So in other words, these will always be dimmer the more you add, and these will be brighter than a series, but definitely brighter. So that concludes the differences mainly between series and parallel. The next video, we're going to combine these ideas.